Okay, YouTube, in this video we are going to confront these special right triangles. We call these special right triangles because the relationships between the sides of these triangles and their inner angles are extremely common. So common that after watching this, I hope you make some flashcards. We're going to populate a table down here for the values of, say, sine, cosine, tangent, and their reciprocals of 30, 45, and 60. But I hope you memorize these values because they often come in very handy when talking about right triangle trigonometry. But we have two special right triangles, at least we call them special right triangles, and these are our 45, 45, 90 triangle and our 30, 60, 90 triangle, okay? And we're going to go ahead and focus on the relationship between their side lengths, but essentially you'll notice that I've already kind of laid them out here where I'm using some variable value a. And so for instance, on our 45, 45, 90, what I can tell you is this: when you look at special right triangles, you always look at the shortest side first, and we'll just call it some value, and I call it A. But I can always tell you that if you have a 45, 45, 90 triangle, for instance, this one that you see right here, these two leg lengths would have to be the same thing because their angles opposite are actually the same things, okay? And I can also tell you this: no matter what, if you have a 45, 45, 90 triangle, whatever the shortest side length is, the hypotenuse is always that number times the square root of 2. It just happens. So for instance, if we were to throw out a 45, 45, 90 here, and I could guarantee you this is a 45, 45, 90 by filling those in, and I say that this is a length of 3, then automatically we could say that knowing the short side would be a benefit here. We could say that's A, this would be A, this would be A root 2. We could say that whatever these legs are, we just need to know the length of the short side here, and so we'd say that this one is also 3. And then this number up here we would say is A root 2, where we know the value of A is 3, so we just get 3 times the square root of 2. That's what it is, okay? Now, on our 30, 60, 90 triangle, we kind of have a similar scheme. Notice that the shortest side is the one that I call this variable letter here. We say A. But I can always guarantee you that in a 30, 60, 90 triangle, whatever the length of the short side is, we'll compare everything to the length of the short leg. I can guarantee you that the hypotenuse is always twice as long. And I can also guarantee you that the longer leg is whatever the short side is times the square root of 3. So again, I mean, I'll throw out an instance here where if we had a 30, 60, 90 triangle, and this is a very poorly drawn 30, 60, 90 triangle, but let's just say, for instance, I told you that the hypotenuse length here was 10 in this 30, 60, 90. Then what we could go so far as to say is this: well, I know that the short side has a length of A, the hypotenuse has a length of 2 times A, and that this side has a length of A times the square root of 3. So if we just knew the length of A, then we would be in solid shape here. Okay, so I think that what I would want to point out is the fact that 2 times A is equal to this 10 up here. So if we were to solve, say, for A, divide both sides by 2, it kind of follows that A would have a length of 5. And that makes sense here. You would say that in a 30, 60, 90, whatever the length of the short side is, the hypotenuse is twice as long. And this length down here, we would just be A times the square root of 3. Okay, so knowing these relationships is very helpful. As a matter of fact, well, I want to go so far as to say that I want to find the sine, cosine, and tangent of 30, 45, and 60 all of the time, no matter what triangle you have. What I can tell you is, it wouldn't matter what triangle you have. If you had a 30, 60, 90, let's say that this is a 30, 60, 90, 30, 60, 90 here, and I were to cut in like another thing here, you know, and I would say, well, now I've got another smaller 30, 60, 90, and now I've got another smaller 30, 60, 90. No matter what, if we were to go say, find the sine of this angle, that is the opposite over hypotenuse, or here we would say the opposite over the hypotenuse, or here the opposite over the hypotenuse. In our small, medium, and large triangles, you're always going to get the same value for the sine of 30. So it is, you know, worth our time to know this value, to find it one time and then know it. So if I want to find the sine of 30 degrees, how would I do this? Well, first of all, I would draw out my general 30, 60, 90 triangle. That is, no matter what numbers I plug in, this is how they compare. And I say, well, knowing that I find the sine as the opposite over the hypotenuse, we say sine of 30. So we could write this out over. We say sine of 30 degrees. We're going to go to our 30-degree angle in this triangle. We're going to say, well, how does the opposite side compare to the hypotenuse? And what we get is this A over 2A comparison. And our A's here, in particular, cancel out, and I'm left with this 1/2. So I can tell you right now, you want to fill this in, but the sine of 30 degrees, no matter what triangle you have, is always a 1:2 comparison. And that makes sense because this side here is always, you know, half the length of your hypotenuse. I mean, this is always true. So if we say, what about the sine of, 45? Now, sine of 45, we're going to have to go refer to our other special triangle here. We say here's our 45-degree angle, but we say opposite over hypotenuse. In this case, we get A over a, whatever that is, times the square root of 2. So our a's cancel out and we get left with this, 1 over root 2, which after rationalizing that becomes root 2 over 2. So the cosine, or the sine of 45 degrees is root 2 over 2. Now the sine of 60, I want to go find the sine of 60 degrees, which means we're actually going to have to go look at this upper angle up here in this triangle. And we say that opposite over a hypotenuse length here would be a root 3 over 2a. So we get a times the square root of 3 over 2 times a, where our a's kick out, and we're just left with this, root 3 over 2. So we're going to memorize this table. Yes, we are. It's just that, you know what, I can indicate a pattern here. All of these things had something in common. They're all over 2. And you'll notice that going from 30 to 45 to 60 with your sine values, it just goes 1, 2, 3. You might be saying, well, this top number up here didn't have a radical on it. These two do. Well, if you put a radical over the top of this, you get the square root of 1, and the square root of 1 is still 1. So as far as the sine values of 30, 45, and 60, they are all over 2, and they all just go 1, 2, 3 in that order. Now let's look at cosine values. Now cosine, a little bit different. Cosine doesn't compare the opposite side to the hypotenuse, it compares the adjacent side to the hypotenuse. So that is to say that if we were to go do the cosine of 30, now up here we said here's our 30-degree angle. Notice this, we get adjacent over hypotenuse, which is just this a root 3 over 2a, and we've already seen this once just above this. Over 2a, we get root 3 over 2. So root 3 over 2, you'll notice that the cosine of 30 is the same as the sine of 60, so we get root 3 over 2. When I do the cosine of 45, we have the cosine of 45 degrees. Let's go look at our 45, 45, 90 triangle. Here's our 45. If we do the cosine of this would be adjacent over hypotenuse. We get our a length thing over a root 2, which is just 1 over root 2, which is root 2 over 2. So we have root 2 over 2 is the cosine of 45. And if you wanted to guess what you think we're going to get here, I might guess that I think I'm going to get a half. But if we do the cosine of 60 degrees, going up and looking at our 60, we say adjacent to our 60 is a, over the hypotenuse length is 2a, a over 2a. There's our half. There's our half. A's canceling out. So what I can tell you is, when it comes to memorizing these values, I always tell people memorize your sine values first. Always, just your sine values. Because they're all over 2 and they go 1, 2, 3 as you go up 30, 45 to 60, and your cosine values are essentially just the opposites of those. They're backwards. Okay, so now let's look at our tangent values, and then we'll just reciprocate all these to get the right side of the table. But the tangent values, I like doing tangent. I'm actually going to start with the tangent of 45 first, and the reason why is because when you go look at your tangent values, remember we are doing TOA to find tangent values here. 45, if you did opposite over adjacent, you notice that you're comparing two side lengths that are precisely the same. So you would get a over a, and the reason why I say memorize this one first is because the tangent of 45 is always just 1, because you have an isosceles triangle. Now as far as the tangent of 30 and 60 go, let's go ahead and find the tangent of 30 degrees. The tangent of 30, let's go look at our 30 here. We say opposite over adjacent. We have an a length thing over an a root 3 length thing where our a's cancel out, and we get left with 1 over root 3. And after rationalizing this, it becomes root 3 thirds. So tangent of 30 degrees is root 3 over 3. And the tangent of 60 finally, and we can fill out the rest of this table following this. But tangent of 60, here's our 60, we do opposite over adjacent. Here we have a root 3 over a, a's kick out, and we get left with just root 3. So I always ask people to memorize your tangents as well, and what I'll tell you is, well, the tangent of 45 is always just 1. As far as 30 and 60 go, you notice that they both involve a root 3. It's just that the root 3 over 3, which by the way is smaller than root 3, it is the smaller of the two values, goes with the 30 because it's the smaller of the two angles. It's kind of an easy way to remember it. And root 3 goes with the 60-degree angle because it's the bigger of the 3, or bigger of the 2. So as far as finding the rest of these, well, these cosecant values are just going to be the reciprocals of our sine values. So the reciprocal of 1/2 is 2. The reciprocal of root 2 over 2, I'll do this once, we say would be 2 over root 2, which is 2 root 2 over 2, which is just root 2. So I get root 2, and then the reciprocal of root 3 over 2 is 2 over root 3, which is 2 root 3 over 3. So I have 2 root 3 over 3. We can flip these around and say, well, then they're just the opposite of what we have here for our sine values. So this is our 2 root 3 over 3 up here. And then for our cotan values, well, the reciprocal of the tangent of 45 would be the cotangent of 45. The reciprocal of 1 is 1. And then these just turn around. When you reciprocate root 3 over 1, it becomes 1 over root 3, which is a root 3 over 3. So we get root 3 over 3. And this one will become just a root 3 when you reciprocate this one here. So what I'll tell everybody is essentially this. Know your sine values. Cosines are opposite. Remember that the tangent of 45 is 1, and that the root 3 over 3 goes with the smaller of the two angles, and the root 3 goes with the bigger of the two angles with respect to tangent. And then all of these are just reciprocals of those. But these are our special right triangles, and these are the trig values of those special right triangles that you should memorize. Cheers.